The subject of this video is the cardiac cycle. If the electrocardiogram gives you information about the electrical activity passing through the intrinsic conduction system, the cardiac cycle is what we use to describe the physical events that occur during an individual heartbeat. These physical events are things such as the contraction of the chambers and when, the opening and closing of valves, the passage of blood through the heart, and the changes in pressure and volume that we see in the chambers and in the great vessels. So the plan for the video is to go through the individual steps of the cardiac cycle and discuss the pressure and volume changes that occur during each stage. So we start at the first step, number 1. This first stage is called ventricular filling. What is happening is that blood is passively passing from the atria through the already opened atrioventricular valves, mitral on the left, tricuspid on the right, and we are passively filling the ventricles. During this stage, both of our chambers are in diastole, which means that the muscle is relaxed, and the volume in the ventricle is increasing. In the pressure, the left ventricle pressure is somewhat stable, and that is because when the heart is relaxed, the chamber is not completely occluded. We have an empty bag which we are then filling with blood, and then even when we start to stretch the ventricles, we don't see much change in the way of pressure at this stage. And the same would be true for the atria. So in pink we have the atria, in blue the ventricle. The last part that we are interested in is the pressure in the great vessels, and we normally are looking primarily at the aorta. The pressure and volume changes that we see, these graphs are going to be what we see in the left side of the heart. We would see these changes in the right side of the heart, but the values themselves are much, much lower. At the end of passive filling, the ventricles are filled with blood and they've been started to be stretched, and the firing of a pacemaker potential from the SA node is going to initiate atrial systole. So in atrial systole, the atria actively contract down and they are pushing the last bit of blood into the ventricles. So the volume takes a little bit of a kick. The ventricular pressure has a little bit of a bump in it. The atrial pressure also has a slight rise, and that is because when we look at the relationship between pressure and volume, we're using the equation P equals 1 over V. Pressure is 1 over volume. So when the pressure goes down, the volume has increased, or we have the causal relationship the other way round. So here, as the atria contract, the volume decreases in the atria, and so the pressure within them increases. At this stage, we are still seeing a gradual fall in pressure in the aorta. Now, this stage here, I'm going to put number 1 down here, this stage here of atrial systole has been described in a couple of different ways numerically. We can either call it stage 2 or we can call it stage 1A. I'm going to call it stage 1A here for consistency along with the textbook, but you can also see it described as stage 2. The next stage is 2A and is the first part of ventricular systole. Now, what is happening here is that the atria have contracted and we close the AV valves at the end of atrial systole. Now, the problem that the heart then has is that the blood that is sitting on top of the semilunar valves is a barrier to fluid ejection from the heart. It is providing a downward pressure onto these semilunar valves. And so this blood from the previous heartbeat has to be physically pushed out of the way for you to eject blood effectively out of the ventricles. For this to happen, especially in the aorta, the pressure in the ventricles has to be equal or greater than the pressure seen in the aorta. And the problem there is that while the pressure in the pulmonary trunk is not massively high, it's only about 20 mm of mercury, in the aorta the pressure is around 80 mm of mercury. So we have a much higher pressure that we need to match. And so we need a stage of ventricular contraction called isovolumetric contraction. And during this stage, the muscle fibers in the ventricles tense. They don't shorten, but they tense. So there is no change in volume because we have not seen any physical shortening of the fibers. However, we do see a massive jump in the ventricular pressure. Also, because this pressure, the blood is being pushed upwards, we will see a bit of a kick in the atrial pressure because that will reduce the volume in the atria briefly. And our aortic pressure still hasn't changed yet. It's coming down to meet it. Let me just indicate here at the end of our 1A that this is where our AV valves shut, and this is associated with our first heart sound, S1, known as the LUB. So we have tension. The muscle is tensing to massively increase the pressure. Now, when the pressure is then greater or equal to the pressure, the back pressure being applied on those semilunar valves, we can go into full ventricular systole and eject blood by pushing those valves open and forcing blood out of the base of the heart. So we have a massive ventricular contraction and ejection of blood out into the great vessels through those open semilunar valves. And notice that the AV valves are still shut here. So this is ventricular ejection. And this is part 2B. So we have 2A here. In 2B, because we are actively pushing the blood out of the ventricles, the volume is going to massively decrease because we are contracting up and in. So the contraction is a squeeze out of the top. So the pressure here will go up before it comes back down again. The atrial pressure actually stays low, and the atria are now going into diastole, but because of the dramatic pressure changes here, there is no change in blood flow into the atria yet. There may be a little bit of blood returning to the atria, but not masses. The aorta is going to see a huge jump in pressure, and that is because we are matching what has happened in the ventricles, and we have a bolus of blood being pushed out through the great vessels, forcing pressure on the walls and stretching them. So the pressure massively increases. So in that period of time, between these two sections, between this early ventricular systole and late ventricular systole, right here is where we will see our semilunar valves open. Once we have had full contraction, we are then going to see the ventricles go into diastole. And we can break this down into two sections. The first section is called isovolumetric relaxation. Metric relaxation. And the key here is what is happening with the valves. It's actually the changes in the pressure within the ventricles and then the closing of the semilunar valves that really distinguishes this part of ventricular diastole from the next part. So this is stage 3, and what is happening is that as the ventricles begin to relax, you have to imagine that equation, P equals 1 over V. So the volume increases and the pressure decreases. So we start seeing a suction backwards towards the heart, and this backflow of blood will cause the semilunar valves to shut. We will also get what is known as the dichromatic notch. It's basically a jump. When the blood backflows onto those semilunar valves, it actually bounces back up again. So as the ventricular pressure is dropping, the aortic pressure does a weird little kink. It actually does this weird little bounce up to here before it will then start to drop. The atrial pressure, remains low, and our ventricular volume at this point is still low, because as yet we have not opened the AV valves, but we've had the start of that relaxation and the closing of our semilunar valves at this stage right here. So the semilunar valve shuts, and this is our S2 sound, our dub. So S1 is lub, AV valve shutting. S2 is the dub, the semilunar valves shutting with the backflow of blood. The last stage is our ventricular diastole, or full ventricular diastole, otherwise known as late ventricular diastole. You can also call it ventricular relaxation. And during this period in stage 3, as the heart has started to relax, not only did the blood suction and draw back blood through the great vessels to close the semilunar valves, it also encouraged blood to start collecting in the atria from the veins and the vena cava. And so part of our venous return is actually negative pressure suction towards the heart as the ventricles start to relax. So when we go into full relaxation, that blood will then go through into the ventricles and will actually mix a little bit with some of the blood that was left over after ejection, because not all of the blood will ever leave the ventricle. And then we will go into passive filling from there. So the pressure continues to drop in the ventricles. Our pressure in the aorta is dropping. We see a slight bump in pressure in the atria, but not very much, and that bump in pressure is from the blood suddenly being allowed to be released. We get this sort of boom, and the volume will start to climb again. So it starts to climb up. And then the cycle is going to repeat. So our cycle is going with this direction here and is continuous from one heartbeat to the next. So to summarize, we start with ventricular filling, where we passively fill the ventricles. We then have atrial systole, pushing the last bit of blood into the ventricles. We have isovolumetric contraction, where we tense, and please note both sets of valves are shut, so blood is trapped in the ventricles to allow for the increase in pressure. When the pressure is great enough to open the semilunar valves, we have full ventricular ejection, shooting blood out of the top of the heart. We then go into isovolumetric relaxation, where the ventricles start to relax and the negative pressure produced in the chambers not only draws blood back through the great vessels to close the semilunar valves to prevent backflow, but also draws blood into the atria. And then the ventricles fully relax and the AV valves open, and blood for the next cycle starts to flow into the ventricles before we move back into passive filling. So one thing that I did miss here is the opening of the AV valves, and that is in the transition from isovolumetric relaxation to our ventricular relaxation, or our ventricular diastole. So this is the full cardiac cycle. Hope it made sense.